Boa tarde. Hi, how are you? Well, as you can realize, I am not Professor Kazu. I am Suane Coelho. Unfortunately, Professor Kazu, a couple of days ago, had a health problem. He's okay, but he could not come. So we are going to start this section, and then we will have Professor Pacelli Zita, Professor and Chair of Production Systems and Director for Geoscience and Engineering Laboratory at Delft University of Technology. Thank you very much for coming. And we'll have also for the Brazilian counterpart, yes, Dr. Pedro Vassalo. Pedro is currently postdoc student in the Department of Mechanical Engineering of Polytechnic School of USP, with a doctoral degree on energy planning at Federal University of Rio, and today working for the company Modecon. Okay. We will have these two presentations from Professor Pacelli Zita and from Pedro Vassalo. And then following this, we will have a section for discussions headed by Professor Giulio Meneghini to conclude the workshop. Okay? So, please, Professor, you have the floor.
Okay. Now, good afternoon. Boa tarde. I hope I can keep you awake after such a nice lunch. In the Netherlands, we don't have this type of lunch. Huh? Anyway, now before I go into my talk, I would like to thank the organizers, especially Professor Giulio Meneghini, Professor Suani, and all the people that have been involved in the organization of the workshop. I feel very honored to be here, and I hope that it will also result in further contacts and collaboration in future. Now, carbon capture and storage. Actually, the speakers this morning, they already gave a very nice introduction to the topic. They mentioned some of the things that you will see coming back in my presentation. We didn't speak to each other, so maybe that was a nice thing to see that. I'm going to talk about specifically about the Dutch experience, and I will try to connect that to the pre-salt fields in Brazil towards the end. I was told I can control this. Let's see. Yeah. Now, I'm going to pass very quickly through this figure. This is a very famous figure that comes from IPCC report in 2006. It's a little bit dated, but in reality, it's still what is the guiding, let's say, it contains the guiding ideas for CCS. We have different alternatives for storing CO2 or sequestering it. And what I'm going to focus upon, we did some work on storage in aquifers, in depleted gas fields. I'm going to talk mostly about depleted oil fields, and that's because of the link I want to make with pre-salt reservoirs. To start, the experience in CCS in the Netherlands was crystallized in a large project called the Keto-2. This was a large research and development program. Actually, it started as a project for the demonstration of the full CCS chain. And for reasons that I will explain in a minute, that were mentioned also this morning, among others by Martin, it was changed into a research and development project. It was a project with many partners, and it was coordinated by TNO, which is the Dutch Applied Research Institute that was mentioned previously. So just to give you an idea, actually we didn't start in 2008 or 2009. There was already a tradition of doing research on CO2, which was initiated and led by the University of Utrecht. It was a fairly modest effort compared to the Cato project, with 17 partners, mostly scientific organizations. And later on, we started. It evolved into the Cato program, as you can see after the publication of the IPCC report, which was kind of signaling the urgency of dealing with CO2. And as I said, this was coordinated by TNO, but I would like to acknowledge all the parties that were involved. As you can see, this was a huge effort with companies and also universities all over the Netherlands involved. And now, the Barendrecht project, I heard from my colleagues, and I'm going to contradict them, it was not a disaster, it was an opportunity to learn. Yeah, it was technically a very well thought project, very well planned from the technical point of view. No, so people, now it was intended to be a first large-scale demonstration project, and then it was dictated by the existence of a capture plant very close to a sink for CO2, which is in the town of Barendrecht, close to Rotterdam, so about 40 kilometers away. So it was intended as a test for transportation and storage of the CO2 with two stages. The first stage, the first phase, with 0.8 megatons of CO2, 0.2 million tons of CO2 that would be stored in 3 years. And then after that, a larger amount of CO2 would be stored over a period of 25 years. As I said this morning, this project was not conducted because of lack of public acceptance. And I think that was a very good learning point for politicians, but also for the companies. As was mentioned towards the end of the session in the morning, one important aspect is really to have the public along with us in the planning phase. That was a very important learning, which actually didn't sink in yet completely in the minds of everybody involved. Now, there is a project that is actually an ongoing success, and that is a project, it's a small scale compared to Barendrecht, and this project is it's called K12B, and in the North Sea, and basically in this project, CO2 separated from natural gas is stored into the same reservoir. Okay, so this was a unicum, the first time that this was done in the world. And up to now, 60,000 tons of CO2 have been stored, and it is still ongoing. I think the field has changed hands. It was run by GDF before, but now it's with another company. But it's an ongoing project, and it was a technical success, and also from the economic point of view, we can say that it is successful. It's a completely different story, though, than storing 100% CO2. And then we have the ROD project, which is, well, an acronym for Rotterdam Capture and Storage Demonstration Project. There is offshore a gas field, which was run by a company called TACA, some 20 kilometers away. And then, well, the most important thing, or the status at this day, is that there has been a license to store the CO2, which took endless time, I think more than 3 years. But the project is not yet realized. There have been quite some delays, and some of the parties have decided to divest from the project. But with the current climate, it is possible that the project will go ahead. Now, the lessons learned, because that's what we as engineers have to do, is that when we do stuff and they work or they don't work, hopefully, preferably we want them to work, but when they don't work, we have to learn from them. Now, first of all, the most important lesson that from all these projects was learned is that the CCS has to have a position in the overall strategy of the development of the country, which is now for the Netherlands much more clear with the recent climate agreement, as was mentioned earlier today. Now, societal, legal, and economic aspects are actually much more important than technology. Usually we master the technology. We have the science, we have the people that can actually realize the project, but very often we postpone the societal aspect and legal and economic factors, which are actually critical for the success of the project. So, but over lunch I learned that you also have that in Brazil. Now, what I want to focus upon now are the technical aspects, because that's my area of work. What are the lessons learned? What is important for these projects to be successful? Now, the first one is that if we do a project, a CCS project, we need to be clear about the overall goals. So in some cases, so if you're going to inject CO2 into an aquifer, for example, you cannot expect to have any other benefit. So the cost factor will be very important. If you inject CO2 into a gas field, a depleted gas field, you could have an additional benefit which will come from the pressurization of the reservoir. If you inject CO2 into an oil field, you can have an additional benefit which will be the production of oil, of additional oil. And that can offset the economy, the cost, and can play favorably for the economics. One essential thing, because we are at university here, and I hope that I can interest some of the students and the younger people to work in this topic, is the knowledge about the reservoir. So we have to know the reservoir not only in terms of the behavior in the long term, but we have to know the behavior of the reservoir from the smallest scale up to the reservoir scale. It's absolutely essential. And those who work in reservoir engineering, for example, you have a lot to say concerning CCS. And then now, this morning I heard something. I think somebody asked a question of the leakage of CO2. I want, by the way, to correct one thing that was stated right at the beginning, is that the CO2 can leak through faults and etc. There has been no proof of that. Okay, potentially that's a risk, and we as engineers, we have to manage that risk. We have to make sure that it never happens, but there has been no proof for that. In order to make sure that it's not going to happen, and that I agree with my colleagues that spoke this morning, we need to make sure that the cap rock of the reservoirs where we are going to inject the CO2 are sealing. That's as simple as you can explain to anybody. But yeah, the work to do that is quite involved. So, for instance, depending on the type of rock that you have, you could dissolve the rock or not. So, knowing the mineralogy of the sealing fault is absolutely essential. What is also essential is that when you produce a gas field, for example, you depressurize it, and then if you inject CO2, you pressurize it again. It's very important to know what will be the geomechanical behavior of the CO2. So we have to do studies for that. Now, well integrity again, but really in terms of the hardware, what you see in the picture here are different types of completion. I'm not going to go into detail, but uh, the way in which the wells have been constructed is absolutely essential to make sure that they are not going to leak. They will stay there for as long as the CO2 is present in the reservoir. Now, I already spoke about additional benefits in the beginning. So in every CO2 project, CO2 CCS project, we have to ask ourselves, can we draw some kind of additional benefit? And obviously, in gas fields, the additional benefit will be the pressurization of the reservoir. In oil fields, the additional benefit will be the production of oil. But in the Netherlands, by the way, this is an amazing image. So some students, they were at the TU Delft, they'd been drinking one Friday. And after drinking, I don't know how many beers, they said, well, we have to start a project. We want to drill two wells in the campus for geothermal. So one well will produce hot water, which will be used for the installations at university, and the other one will be used for reinjecting the water into the reservoir. And that has been going for about 10 years. And the wells are going most probably to be drilled in the coming 2 years or so. And this is a study that was done to understand the different layers underneath the buildings of the university, because that's where the water will be extracted from. But along with that, we thought that because we are going to re-inject the water into the reservoir, we can just combine the water injection together with CO2. Yeah, so that's another way of having additional benefits. Now, it was mentioned this morning by different people that we can store CO2 in caverns. I think this is also work that is ongoing here at the Institute. Now, these caverns are currently being used. So in the Netherlands, these caverns are made by dissolving salt. So hot water is injected and salt is dissolved until we get a cavern in size comparable to, I don't know, the Eiffel Tower, to take one measure, or a Christ Rey in size. And these caverns are used for energy storage, for hydrocarbon storage, and they are being considered also for the storage of hydrogen. And they can be very good for CO2. The advantage being that we can not only store the CO2, but we can inject some minerals that will react with the CO2 and sequester the CO2. Well, not forever, but for a long time. Now, I would like to link what we have just seen to the Brazilian pre-salt fields. So first, I would like to stress again that there is in the Netherlands CCUS knowledge and innovation program, and then we can build on this knowledge to create a network where Brazilian and Dutch side could have mutual benefit. And I think that we have some demos in the Netherlands that could serve for that purpose, and hopefully we can, by that, create CCUS for future generations. Now, in Brazil, this is, I think most of you probably know this map, but we have a huge, Brazil is a kind of oil province in itself. Yeah, so we can talk about pre-salt, but there are also many other fields that are not pre-salt. And let me go. So we were discussing over lunch that, well, all the companies involved here have been contributing. I think this is a graph that was made maybe 1 year ago or so. And the idea is that, well, there is There is an ambition to ramp up production to 2.6 million BBL per day. Well, I'm not looking at the statistics every day. I'm not so sure if this was reached or not, but it is a huge amount of production of oil, and 1 million plus million BBL a day would come only from the pre-salt. Now you will see in the next slides why this is a problem. Now, for example, from the Santos Basin, yeah, this is a typical FPSO that is using for this development. Now we have, so there is a huge amount of gas that comes together with the oil, and a large percentage of that gas is CO2. Yeah, and then now here I put some numbers just for those who are not really familiar with this. Now, first of all, we have the reservoirs that are at really extreme depths, from 5 to 7 kilometers below sea level. And then not just that, I think we have here almost 2,000 meters of water. And then we have the, let's say, the reservoirs that are already under development, the post salt reservoir, and then we have the salt layer, and here we have the pre-salt. So it's, and some of the fields are mentioned here, Libra and Tupi in particular, are the ones that are mentioned more often for this. And light oil, the content of CO2 varies from 0 to 40% of the total amount of gas that is produced. Now, people have to do something with the gas, with the CO2, because I think the regulations of the Brazilian government do not accept that this gas is all vented. Yeah. So what do you do with it? Up to now, the idea has been to re-inject the gas. So, I mean, hydrocarbon gas together with the CO2 and etc. But if you do that, I'm not going to go into the detail, but very quickly you can have that gas coming out. So the amount of gas produced will increase very fast, and there has to be a solution to that. One solution could be to use to alternate gas and water injection, for example. I'm not so sure if this is being done in the field, but it was discussed. And well, so if we link this to what I just said, to the CCUS experience, we can think about the problem in this way. I like very simple schematics because they kind of tell what is it. So here we have, let's say, the pre-salt reservoirs with what we call confining layers. And of course, in the production wells, we will have CO2, oil, and brine, salt water. And we have to separate the whole lot. And again, this separation has to take place in a very limited space. And the floating units that I've shown you, called FPSOs. And then part of, so obviously we want the most valuable products, the oil that has to be produced. And then we have here the gas. And now part of the gas will be injected here. So the CO2 will be injected into the reservoir. And as I said to you before, it's just it's a fairly simple calculation to estimate when the gas will reach the production well again. And then the gas that is separated here is actually has also value because it's hydrocarbons with CO2, with a lot of CO2, but hydrocarbons. And then it can be burned to produce electricity. And then part of the CO2 will also be injected in the reservoir. Now, there are several options to use the CO2, or at least to apply it. The first one is what people decided to do is the most straightforward, is to re-inject the gas, CO2, or maybe CO2 with hydrocarbons to displace the oil. But again, I already mentioned what problems that could cause. The other one is to use what we call cyclic injection of CO2. We call it also huff and puff. And so you inject CO2 for a certain time, you let it contact the oil, and after you produce the whole lot, you separate the CO2. Now, you cannot do this indefinitely because this chamber will grow, and after some time, different chambers will contact each other. And then you have what we call water alternating gas, which is a little bit more difficult to implement, but it can correct all the problems that are linked to this one here. And now, yeah, what what makes CO2 so attractive? What makes CO2 injection attractive is that when the CO2 contacts the oil, CO2 tends to dissolve much more in oil than in water. So it swells the oil, and you can really produce much more oil. And hopefully, you can also store part of the CO2 into the water. All these reservoirs contain a lot of water. And then, yeah, we use this called storage efficiency, which was defined by Blunt and co-workers. So your storage efficiency should be high enough for this to be considered a CCUS project. Now, I would like to summarize my thoughts. Now, first of all, now we have huge reserves of oil with associated gas in a very difficult environment, offshore and 300 kilometers. And then now the existing platforms, and this is the opportunity, the existing platform could be a very good place to test technologies for both separation, injection, monitoring of the CO2, whether we do this into reservoirs or into caverns. And then because we are offshore, solar and also wind energy could be combined together with the storage, with separation and storage of the CO2. And then we have to do it on site. We don't have to bring the CO2 to shore, which is very, very cost effective. And then, yeah, so the CCS experience that both the Netherlands and Brazil form, in my point of view, a very strong basis for cooperation and for developing knowledge and technologies to realize what we just said in the previous slide. And then, but we have to consider one limitation at the start is that the majority of the programs on CCS, they've really focused on putting the CO2 in the ground and leaving it there for 1,000 years, 10,000 years, or 100,000 years. And what we really need is a shift in thinking where we are going to store the CO2, yes, but we are going also to find ways to use it, for example, to generate biomass. I don't have any concrete ideas, but we have in the room people that are specialized in that topic. And I'm pretty sure that if you would have a free source of CO2, you would know what to do about it. And now, before I close, I would like to acknowledge the people that actually form the fact that I'm, the co-workers, colleagues that have been working on this topic with me over the years. And in particular, Karel-Heinz Wolf, who was together with me the coordinator for that reservoir behavior studies in the CATO program. And then these are, they're not junior anymore. They all graduated, at least most of them, former PhD students, postdocs, and etc. that did most of the work. And that's all I wanted to say.
Thanks, Professor Zita. We are moving directly to Pedro Vassallo, who is going to talk about the Brazil experience with CCS, perspectives and challenges, and then we'll come back for the discussions.
Okay, good afternoon, everyone. Firstly, I would like to thank Professor Júlio Meneghini and all my colleagues from RCGI for the opportunity. And thank Professor Pacelli because he made a very big favor for me today. You showed some information that I cut from my presentation because it was too big. And I think you'll find this interesting, okay? And one interesting point is that in the discovery well of Lula Field, Santos Basin, it had the same content of CO2 of this field K12B, Pacelli mentioned. It was the same situation. Okay. So just giving a very quick introduction on underground gas storage. This is the basis of our project, the project 34 from RCGI. There are mainly three, the most important technologies for underground gas storage today. There are these three here. So, where is the laser? This first one here is, this first one is based on porous rocks, so aquifers and depleted reservoirs. The second one is salt caverns. This is the key for the deliverability in the entire world. And also mines, abandoned mines, reverted for the objective of gas storage. And the main ones that are being used and analyzed to be used as gas storage are salt mines. Well, the choice for one technology or another, it's because of several reasons. Most of them is because of occasional and technical reasons. Okay, so salt caverns, for example, is a more expensive technology because you need to open the cavern and invest in the whole infrastructure, but it has some advantage, technical advantage in comparison of the other technologies, especially related to the deliverability. So higher rates of gas injection and withdrawal, okay? And I will show some outlook of the underground gas storage market. Most of the facilities today are the depleted fields. The second one are salt caverns. There are some other in aquifers. This technology here is falling to being used. They are being abandoned because of some environmental aspects, okay? But even though the majority of the market today for underground gas storage are covered by depleted fields, the new projects that are under development or being studied considers more salt caverns, okay? Because the key now is deliverability. And so if you look the market as it is today, okay, in working gas capacity, the salt cavern covers only 32% of the entire gas storage in underground facilities, okay? But when we talk about peak withdrawal rate for the new project, salt caverns covers 47% of the delivery, okay, of gas. Another interesting point here is that the salt caverns correspond today for only 80.5% of the working gas capacity for storage, but correspond for 25% of the global deliverability. Salt caverns can be cycled several times a year, okay? When depleted fields mostly can be cycled just once. even though they can store much more gas than the salt cavern because of its size. But it's slower. The withdrawal rate is lower than the salt cavern. I think I covered this already. So, giving continuation to the Professor Pacelli presentation, this is the environment of our project, the motivation to our project. Today, the CO2 found the pre-salt reservoirs, they have a mantle origin. They migrate from the basement of igneous rocks through rock faults to the pre-salt reservoirs, and it is continuously feeding the reservoirs with CO2, okay? And one option that was thought to solve this situation in the past, in the beginning of the pre-salt exploration, was to reinject this gas with high content of CO2 in aquifers in the pre-salt region, above or under the salt layer, okay? But it was found two problems. Above the salt layer, we have the problem that the sedimentary cap rock has a small thickness. So it won't support the amount of gas that would be stored with safety. And the other problem is that if this is what is going on today, if you reinject the gas with the high content of CO2, again, in the reservoirs, in the future, we will increase volume of CO2 in the reservoir. So today we are already hearing problems that some wells might be closing or are close to stop to the production because the volume of CO2 is very high. It's too high for the membranes to separate, okay? So with these boundary limiting conditions of the pre-salt scenario, pump up the idea to store this contaminated gas in large salt caverns built in the salt domes in the pre-salt area, okay? And this is where our project is based on. Even though you can use this contaminated gas for EOR, enhance the oil recovery, as Professor Pacelli said, it must be done under a specific strategy. And because if you don't do this way, you can compromise the oil recovery in the fields in the future. Okay, you keep much of the reserve inside the reservoir. You can extract this in the future. Okay. Here's presents some characteristics of the salt rock that make this geological material very good for underground storage of hydrocarbons, gas and oil and derivatives. It has negligible porosity and permeability, even under very high pressures. You will see in the next slides, our project, it covers a very high pressure. The sealing, it's an excellent sealing for fluids and gases because of this characteristic. The creep effect makes it self-heal, cracks and microfractures. So it's safe to do the storage. It's soluble in water, as Professor Pacelli explained, so we can build a cavern easily, even offshore in the pre-salt region. And there are some specific salt rocks that are more suitable for the caverns construction. Okay? And the salt caverns, they have the ability to form these geological formations here, domes, diapas, that are the best formations to build the caverns. Okay? So here we go with our system. This is a general overview of our project. Here you can see the FPSOs, okay, in operation, producing oil and the gas as well, everything. Here is a drill ship, and here is the pre-salt region, okay, the seabeds and everything. So this is not in scale. We have another overview that is in scale. This is not, but it's easier to see how it works. So basically, the platforms, they will produce the gas, contaminated and everything, and then it will be, instead of being reinjected on the reservoirs, it will be injected on the caverns, okay? And the first idea was to also make the separation of the methane and the CO2 inside the cavern. I will explain this better in the next slides. But today we are studying only the storage of this gas here and abandon the cavern in the future, or if we find out a way to monetize this CO2, better, right? And this is the overview, all the subsea equipment and so on, okay? For the construction, the idea is to use a drill ship only to drill the well for the cavern construction, and then you install a subsea pump to inject the water and do the leaching process. That is the process that builds the cavern, dissolving the salt rock, as Professor Passara explained. This is the leaching process. Basically, it uses a well, of course. You put inside this well 2 tubes, one larger than the other, and you intercalate between them. We call reverse leaching and direct leaching. You pump inside the well through the rock salt water. Salt can be salt water for the ocean, of course. And you will withdraw the brine from the annular between the larger tube and the smaller tube, okay? And between, in the annular, between the well and the larger tube is compressed some synthetic fluid just to protect the top of the roof of the cavern, okay? The cavern is built from the bottom to the top. So you drill the well until the depth of the bottom of the cavern, and then you start to dissolve the salt from the bottom to the top. And the top is protected here, you see? So the size is limited to this area here. You can do this by vertical wells or directional wells. It's, of course, it's necessary to have a very strict well project to resist both stages, the construction stage and later on the operational stage phase of the cavern. It's used during the construction 3D scan sonar to be analyzing the geometry, the evolution of the geometry of the cavern during the construction to see if this is working as planned. Sometimes you have some intercalation of different rocks, and it can compromise the geometry of the cavern. So some techniques must be done, okay? This is a real image of 3D scan of a salt cavern in the northeast of Brazil. And this shape here is perfect for gas storage, okay? It has a very homogeneous, you see, cylindrical, and they have a slenderness rate that it's good for gas storage. You can also build this cavern using 2 wells. Basically, you use the both wells separately in a distance that after a while, when you start to build the cavern separately, they will intercept and build only one big cavern, okay? And it make the process faster, but it's necessary to have a more controlled operation, okay? Once you finish the solution and the cavern construction, you inject the gas inside the cavern, you pressurize the gas, and it will compress the brine, and it will come out, will be withdrawn from the cavern by the wells. Using 2 wells, you can inject the gas by 1 well and withdraw the brine through the water. And if you use only 1 well, you can use the annular between the larger tube or the well wall and one of the tubes, okay? This is a very made-to technology. There is no innovation here, okay? It's being done in Brazil and many other places in the world, especially North America and Europe. Okay, now we will present some results of our group, our Project 34 group. So recently we did a parametric study to establish a relation between the time spent to build a cavern that would be required to build a cavern and the volume of gas that could be stored in this cavern, okay? And we, of course, we based the analysis on parameters discussed with the group and Shell. And the cavern that was concluded from this study was this one here that has average diameter of 93 meters to 275 meters high, okay? And only this cavern here, just to have an idea of volume, considering expansion factor of the gas in this in the location of the cavern of 577, the geometrical volume of 1,700,000 cubic meters of the cavern, it would be possible, multiplying those values, of course, it would be possible to store 1 billion cubic meters of the contaminated gas in standard conditions inside this cavern here. This is a complete basic project of the well. It has covered the same standards and definitions of the currently pre-salt wells, okay, the same procedure and everything. It was also a result of this study. Here is the cavern. And here it's analysis that was done through salt gas simulator. This is a simulator for the leaching process, okay? And here you can see the evolution with time of the size of the cavern over the time of construction. This cavern specifically, it would take 600 days to be built. Of course, under the design basis we considered, okay? For example, the flow rate of seawater injection was 960 cubic meters per hour. Here is, we try to put this in scale, just to have an idea of the size of this cavern. This is a highlight dome. Okay, here you can see the pillars between the caverns. The slab protection. Slab protection is a layer of salt that is kept over the top of the caverns, just to maintain the structural integrity of the system. Okay, here it's presented a typical Christmas tree that is used for the leaching and also for the operation process. This is the software that was used for the geomechanical structural analysis of all of the results of the project. This is a mature technology. It's been used in Brazil for close to 40 years now. It was used in several salt cavern projects in northeast of Brazil and also in hundreds of pre-salt wells. Okay, it's based on the finite element models. And this is the simulator. It was developed by Professor Álvaro in the between the 70s and 80s. And we use a post and pre-processor, CAD and Kai, together with the simulator, okay, the numerical simulator. And here's only some technical data of the simulator. So here it's presented the withdrawal of brine by gas injection of this parametric study result. This is the evolution of the process with time. So here you see it would be replaced only this size after 114 weeks of gas injection. Then 128 weeks, that would be the probable scenario, 142 and so on until the cavern would be completely full of gas, okay? This is an output image of the numerical simulator coverage. This is a simulation that was done for the radial displacement of the cavern walls during 30 years, okay? So, of course, it covered all the stages of the system, the construction phase, the replacement of the brine by gas, and then the cavern abandonment. This is a simulation. Here is some design basis that we are using on this project analysis. So this is a ISOPAC map of highlight. Here you can see in this red color good zones to build the caverns. It represents that in these areas here you have a homogeneous rock, and we know now, after of course a while of pre-salt exploration, that it's some areas it's pure highlight, which is the best rock for the construction of the caverns, okay? And here it's a seismic section showing a salt diaper, a saline dome, where the caverns are built. This is the best geological formation to build the caverns, okay? This is, here is a result of another study that we did under the project. This is a big cavern that would be able to store a big amount of CO2 or the gas stream that will be considered in the future. So just to have an idea of the pressure inside the cavern, the maximum pressure would be 450 bars. It's a lot of pressure, of course. And this cavern here would be able to store around 7.2 million tons of CO2. Okay? And considering the data that, hypothetical data that was passed to us in the beginning of the project, the volume of gas that would be stored day by day, it would resist for close to 4 to 6 years of 1 FPSO production. Okay. We also studied the development of experimental cavern, small size, just to take some parameters, you know, test some features and technologies, and then build the full-size, big-size cavern. Okay. This cavern here, we decided to make it with 48 meters high. It's a small cavern, and with a diameter close to 20 meters. Okay. And this slide here is to show that it was not good. The image is not that good, but if you, this is a big cavern here, and if you look here, this point, it's you have the experimental cavern inside. The idea here is to show that all the infrastructure that would be invested for the experimental cavern won't be lost. We could later on build with the same infrastructure a big cavern, okay? After we had all the data we want. And here is the final stage, our final goal with the project. Actually, it was the first concept. We last year deposited a patent on this. And the idea is to make the CO2, CH4 separation inside the cavern. We call this gravitational separator because we analyzed that under a specific state of pressure and temperature of the cavern, the contaminated gas, the CO2 would go to the supercritical state, and the CH4 and the other gases would stay in the gaseous states. And it would make a natural separation inside the cavern. And you would be able to separate very big volumes of gas. Today, it's being done by membrane, what is a very expensive technology, and it possibly would make it cheaper because we would be separating very big volumes. And how it would work? The system would work by relaxing the pressure inside the cavern until the point that the CO2 starts to become gaseous again, okay? So you relieve the CH4 until a certain pressure, then you stop, start to pressurize again with the contaminated gas. The CO2 will go to the supercritical states and so on, so on, so on, until the cavern would be full of CO2 and you close it and abandon it. Or use for other objectives. Here, using what Professor Pacelli said, this is just to show that the big size cavern you were studying is not unusual, okay? It's a big cavern, but there are even bigger caverns in the world today. This is a storage facility in Germany, the Nottenmoor underground natural gas storage. And this is one of the biggest in the world. And in this facility, the caverns have a size of 420 meters high for 80 meters in diameter. Okay, and here it was a figure that I made for my PhD thesis, where I just showed how big was that, and I put some Cristo Redentor. The original was the one Professor Pacelli mentioned at the Torre Eiffel, but I make a Brazilian version, Professor. Okay, and okay, and that's it. Here is another comparisons. This is the size of the Northeast South Cavern, the Brazilian Northeast South Cavern that I showed in previous slides, in Salgema Mineração. This is the cavern we are studying now. We have studied in the Project 34. And this is the cavern of the Strategic Petroleum Reserve. It's huge, 600 meters high and in average 100 meters in diameter. It is used to store crude oil. And this is another offshore South Cavern storage facility concept. So the idea is also not new. This is a UK project. The objective of this project is store gas, natural gas, to increase the supply safety of the country. And but this is more less complicated environment because this is in shallow waters, 50 meters depth, I think. Or it's into 25 meters water depth and only 25 kilometers from the coast. Okay, we are studying a much more critical condition. So now I will just give you some information that we have in Brazil all the knowledge necessary to develop this project. In the project 34, we have a very strong team with startups and researchers. And in terms of salt rock geomechanics, Brazil has a very long knowledge curve. It started, Professor Álvaro Maia was a pioneer in this analysis. His first studies was on this potash industrial plant here. So it's a very complex project. I don't know if there is someone here from the geomechanical field, but this plant here was supposed to explore sylvinite and halite between two layers of tachyhydrite. That is a very complex salt rock that has a very high creep rate, and it deforms very fast. And several people said that it was impossible. It had also aquifer above the mine. And in the end, it was able to make it happen. Okay? And it was used the same simulators and the same technology we are using today in the Project 34. Okay? And this is another mine that Professor Álvaro Maia worked on. And but this is a different... actually, it's the same mine, I'm sorry. The mining technology of this plant here is not by leaching. This is a conventional mining. Here's just to show the size of the galleries are very big. And this is salt rock. And it's a very complex project, okay? Here is a picture of him, very young, inside the mine. This is tachyhydrite. Here he's showing that the floor heave by the floor heave by the tachyhydrite. So it's pressing the other layer of salt rock up because of the creep phenomenon. Okay. And here is shown after a while the same place, the tachyhydrite almost touching the roof of the gallery because of the creep phenomenon. And when he analyzed it, this is one of a finite element mesh from his simulator. And when he first analyzed the situation, he made a curve of the evolution of this creep situation inside the galleries. And with the time, the results of the simulation hit exactly the same data that was collected in the mine. So showing the precision of the numerical simulation. Okay. And to finish, this is this slide here put just to mention that yes, this is a challenge, this project, but in fact, there will be some new technology that must be developed, adapted, okay? But we have all the knowledge to make it happen. Like the pre-salt, the exploration of the pre-salt reservoirs. I don't know if you remember, but in the beginning of the pre-salt, there was a question, it will be, we don't know if it will be possible to explore these fields. I don't know if you remember the salt challenge, right? It will be impossible to cross the salt. And all that knowledge that was used to make it viable the mine, I presented before, the same simulators and everything were used to make it happen. And today, pre-salt is correspond for most of the Brazilian oil production, right? And that's it. And our project, basically, we need to aggregate the knowledge acquired with offshore deep water exploration and the knowledge with salt cavern for gas storage. And that's it. Okay? Thank you.
Thank you, Pedro. Okay, now I have time for some questions. I give the floor to, please, Professor Zita and Professor Julio. Join. You take care of the session now.
Okay.
No, thank you very much for both presentations, and now we are open for questions. Any question?
Good afternoon, all. I'm Dixon. I have two questions actually. I'm a student of USP. So actually, the question is boiling down from my PhD research interests. So one, I want to find out whether that I want to hear your thoughts about the cement sheet integrity as it relates to the storage. Have you been consider? Have you considered it in your research? And if you have, I want you to also, if you have, I want you to relate it to why is it that most of the presenters emphasized on depleted reservoirs and nobody considered coal seam, for example, and then the deep aquifer? Thank you.
Okay, thank you for your question. I didn't personally study the interaction of cement and CO2, but this was one of the most important topics in the well integrity studies that were led by our colleagues from Utrecht, and the name is Professor Chris Spires. So they did extensive experiments in which they put cement in contact with CO2, and they looked at how it behaves over time. And as you can imagine, life is very complicated because some cements, they can resist to CO2, and some cements, they cannot stand CO2. So you start to create channels inside the cement. Yeah. So it's, again, I think Andre Fay this morning, he mentioned a few times site specific, reservoir specific. So this is very important. Also for cement, it should be a specific study should be done for those conditions. Now, concerning the second and third part of your question, I did en passant mention aquifers. Actually, we did quite a lot. I had a few PhD students and postdocs working on CO2 injection in aquifers. We did modeling and experiments, but the purpose of my presentation was really to link the expertise in the Netherlands and in Brazil, and not to go deep into what we have investigated. Of course, aquifers are also very important storage sites. So, for instance, the Sleipner project in Norway is one of the examples of that. Yeah, so it is important. And coal seams, one of the gentlemen that I mentioned in my presentation, Karl-Heinz Wolf, he has been working many years on CO2 injection in coal seams together with Hans Browning. Well, the idea there was to store the CO2 and to recover the methane. So there is plenty of work that we have done. I think Shell also has done quite a bit of work in that area.
Thank you very much. The last question is related to the economic point of view. Have you considered any economic analysis to like to use as a basis for comparing which technique is better for storing, that's the CO2 in geological sites? Have there been any economic comparative study on the different technique available?
Well, good question, Dixon. Actually, for depleted fields, it's cheaper, of course, than salt caverns. All the infrastructure is already there, so you can use the well and everything. But today we have this problem of the increase in the CO2 content inside the reservoir. Okay, so the reinjection is something that must be analyzed, other alternatives. And now talking about the salt cavern, I think we have a trade-off that makes it very interesting, because imagine the cost for you to close a well. So all the production that will be stopped in reason because of this. Okay. So the trade-off is all the money you lose closing the well instead of build a cavern. Okay, just have an idea. One well of pre-salt has a cost of more than $100 million. And in a first estimative we made, okay, but it still grows. It would cost for build a cavern around 300 million. And so I think the cost so far is not a concern for the project. Of course, it is. Of course, it is, but the trade-off is very expensive. Okay.
Zita would like to complete.
Well, no, maybe talking about the aquifers, storage of CO2 in aquifers. Usually, the cost is not really the main factor. So, in the Sleipner project, the project had to be done, and that was a directive from the Norwegian government, and it was to demonstrate that it would be possible. And well, somebody has to pay for it. Probably the Norwegians paid for it, and we paid for it because some money came from the EU. But I think we should think in terms of cost, but also in terms of scale up. So as the techniques scale up, like for example the caverns, the salt caverns, as you make many of them, the cost will go down very quickly. Yeah, it's a known phenomenon.
Sasha.
Works. Thanks. Also a question about scale or scale in general. I was trying to calculate how many of these salt caverns do you have to build per year to store all the CO2 that we emit as mankind?
That's a good question.
I think that's for homework.
Now, my calculation was a few thousand. Is that correct?
No,
No,
actually, the big cavern.
Yeah. Was a few million tons, right?
Hmm?
Was a few million tons.
Yes, but we are talking about gas stream.
Yeah.
It won't be pure CO2, right?
Yeah, but mankind emits roughly 40 gigatons of CO2 per year.
No, yes, for sure.
Yeah.
But a parameter is that for one FPSO,
Yeah.
one big cavern
Yeah.
would resist 4 years or
Yeah.
more.
Okay.
And the FPSO is really a tiny
Yes.
CO2 emission compared to mankind. So it's probably much more than the number you just mentioned,
Okay.
400 per year.
Probably it's more. Okay, and then one more technical question. I understand that you actually pump up a brine. Yeah. What is done with the brine?
What's being done with the brine?
With the brine.
It's released to the.
Yes, we are understood so far. This is one of the questions we are trying to answer.
But is it allowed to, for instance, just dump it in the ocean, or
Depends. We are actually right now analyzing to maybe pump it in a water depth where there are a lot of currents,
Yeah.
and so it will what do I say,
Dilute.
dissolve in the
Dilute.
ocean. You know?
okay?
Diffuse.
Diffuse quickly.
Thanks.
Yes.
Well, ladies first, and then
Oh, tá falando. Yeah, my question is for Zita. We have been working on this caverns for a while, and there are so many aspects that we did not cover yet. But you mentioned that most of the studies are based on the permanent sequestration, and in order to make this a feasible and safe way, there's a lot of constraints regarding monitoring,
Yes.
and especially in Brazil, we do not have up to this point no regulation regarding this specific issue. What do you see are the main challenges for the monitoring part as a permanent sequestration of CO2 in such a harsh environment as the ones that we are planning on deploy the salt caverns?
So monitoring is a challenge in any type of CO2 storage sequestration. And as a proof of that, the Dutch government and also the Norwegian government. So in the North Sea region, there are quite a number of projects to develop and implement. They are in TRL 3, 4, up to 6, 7. So really not the very beginning of technology development, but implementation for CO2. Permanent storage is first policy. So what do you monitor? How accurately do you monitor it? So that's a government thing. The problem is that the government might not have enough information to make the policy. So a lot of the projects that are ongoing are to gather this information. And I mean, some of the projects are already ongoing, and some will start soon to see how to best what is the best strategy to monitor CO2 storage sites. Yeah. And in the case of cavern, I think that one of the biggest challenges is geomechanics, especially if you think about caverns that are going to be cycled. Geomechanics is, and yeah, it's an area where quite a bit of development still is needed. Although there are some solutions from the 80s, yeah. But yeah, I don't know if you want.
Hello, Daniel from Petrobras. I have a question to Pedro about it seems to me that you have to use a large amount of energy to build those caverns, and I mean, even to keep it or to keep it pumping. Have you ever done a CO2 balance? I mean, I guess there is a volume of the cavern you lose because you have to emit somewhere or somehow to build it. So there is a minimum size. How does it works? How do you consider the life cycle analysis?
Very good question, Daniel. This is a point that is still under study in the project, but the only parametric study, it was not based on life cycle, CO2 life cycle, but only in terms of time to build a cavern and the volume of gas that could be stored in the cavern. And but this is something interesting to be considered. It must be studied for sure. We know that will be needed a lot of energy, especially in the construction phase, to pump the water.
there are some restrictions regarding the keeping waste underground. So I would like to ask if this CO2 that are being collected from oil, from other origins, if they have some waste and how costly it is to get rid of the waste, if this is really a concern.
I'm sorry.
Contaminants.
Contaminants.
Contaminant. Yeah. I can. Yeah.
Okay.
I think I can use this one here. So the gas, if the in the case of the pre-salt, because if we talk in general, in the case of the pre-salt, the gas is actually not the main product. So the gas as a whole is waste, and then you might want to use the gas for power generation, but then you should have less than a few percent of CO2 in the gas in order to use it for power generation. And actually, if you would export it, you should have even less CO2. Yeah. And this is what made, for example, also the project in KB12 necessary and also interesting. The CO2 was reduced from 12 to a few percent, I think 1 or 2%. And the rest, so this CO2 had to be stored somewhere. And the costs, the necessity to reduce the amount of contaminants in the gas was an incentive to make this project. Yeah.
Does this CO2 has some contaminants, or it's clean enough that you can really pump it down underground?
In principle, the CO2 will contain around 2% of contaminants, so other gases, so nitrogen and etc. So natural gas contain. So and it is allowed. I mean, if you store it there, it is okay. Yeah. Clean contaminants. Yeah.
Fabrício from Federal Institute of São Paulo. Gas storage is not my subject, right? But I just wonder how can you control the entrance of the gas into the cavern, because you told about 480 bar, so it's a high pressure. I just wonder how can you control this in the entrance?
Well, there are several. It's already being done, of course, in the pre-salt exploration of the fields. So there is a specific equipment that is keeping measuring the pressure there, actually in the borehole, and you know how much pressure is inside the cavern. Okay.
Yeah, this is the point, because as Pedro said, the pressure now that the gas is being re-injecting the reservoir is much higher.
Yes.
Because it's deeper. It's deeper than what Pedro presented as the depth of the salt cavern. Now is being injected in a much deeper reservoir, and the need of energy is already there.
Very good point. If you see, the pre-salt is above the salt layer, right? It's under the salt layer. So the pressure necessary to re-inject the gas inside the reservoir is much higher than we need to put inside the cavern that's in the salt layer. You see?
Leandro.
So good afternoon. My name is Leandro. I work in Project 34. My question is to you, Professor Pacelli. I am particularly concerned with the long-term exposure of the salt to CO2. So I would like to know if your university has any experience on, for example, assessing solubility of salt in
Into
supercritical
CO2.
CO2. Yes,
In supercritical CO2.
exactly.
Now, first of all, my intuition, which maybe next time I come here, I would say, well, I was completely wrong. But my intuition is that dissolution of salt in CO2 is very unlikely. But to answer your question, those projects of CO2 storage in salt caverns are recent and new. So we don't have data. Yeah. So this is one of the things that needs to be investigated. Yeah. I think just to add to the biggest concern actually with salt, which was observed in salt caverns in the Netherlands, is the creep of the salt. Because when you inject the fluids, it looks like a solid, but over long periods of time, it's kind of fluid.
Any additional question?
Sergio Paca from USP. You mentioned an idea that you pump methane and CO2 together and then you separate the two in the salt cavern. But is there any difference when you, in terms of the energy penalty or the compression, right? The energy consumed by the compressor, if you pump only CO2 or if you pump methane and CO2, the mixture? Because my understanding is that you need much more energy to pump the two together than if you separate before. So I just want to clarify. Yes, maybe you can help us as well.
Maybe this is true, but it's already being done. You see, this gas stream with high content of CO2 is already being reinjected in a very much deeper situation that are the pre-salt reservoirs. So I think in terms of a bottleneck for us, it won't be a critical situation in terms of I don't know if it was what was I respond to your question or not.
Well, just to make sure I understood also the question. So you're talking about the separation inside the reservoir and the energy penalty
Yes, the energy demanded to compress.
to compress. Yeah.
Pure CO2 versus a mixture of CO2,
CO2.
and methane.
Yeah.
Right.
Now just also again intuitively, you need more energy to compress the mixture of methane and CO2 than only CO2. That's obvious. But I think the separation that is taking place in the reservoir is happening, I think, almost for free.
Yes.
Yeah. So it doesn't cost any extra energy in that sense.
Yeah, it would be nice to have the numbers and compare the membrane versus this technology. That's my question.
Good,
Thank you.
Good.
But I can just complete what Professor Pacelli said. Well, you spend a lot of energy through membranes or any kinds of other separator. And the way that has been proposed now to separate it by gravitational means, only using gravity. Of course, you spend more energy to pump the mixture. But to separate, you I would say that you probably spend more energy apart from the fact that you don't have anything to do with the methane at 300 kilometers from the coast. Apart, I don't know, 10 or 20% that you can use for electricity production for the platform. And then you have to store, at least for the time being, methane. You have to store and there is no infrastructure, there is no pipelines, and the consumption of the platforms are less than 20%, I would say, of the total amount of methane that's being produced. And apart from the fact also that you have wells that has a content of associated gas that varies from one well to the other well. You have there are some fields that are producing almost 70% is associated gas that's coming with the and that associated gas that has 70% of CO2, and then you have to balance. Each case is going to be one case, one particular case to be investigated and to see the energy penalty that you would have to spend. Any additional question?
To decrease the energy penalty, I think we could couple the cavern with a subsea separation. So the gas would be separated subsea and reinjected in the cavern.
In separate caverns.
Yes, I don't know if separation at cavern conditions will occur because it will be in supercritical state. Not sure if CH4 separates from CO2 when the mixture is in supercritical state. I don't know. We should investigate that. But if we change the concept, instead of the total separation in the platform, if we couple with a subsea separator, maybe the cavern gets even more attractive.
Yeah. Probably you would have one cavern for CO2 and another cavern for methane. That was the beginning of the idea of this project, is to have different caverns for CO2 and methane.
It would be a system where you make the separation in one cavern and then store the CH4 in the other cavern.
And then have the methane as a strategic reservoir of gas, and CO2 forever in those caverns, at least one. Any additional question? Well, then I'd like to thank you all, Professor Pacelli, Dr. Pedro, and all the audience, and I hope to see you all tomorrow. We are going to start at 9 o'clock tomorrow morning, and then see you all, and thank you very much for all the speakers of the first day of this meeting. Thank you very much.
Thank you for a nice presentation. Eu percebi também que eu não estava lá.